All right, and our last speaker for this morning is Nick Barrett from University of Paris-Saclay, who will tell us a little bit more about these titanium nitride hafnium zirconium oxide interfaces.
Thank you, Lane, and it's great to be back in the DC area for this workshop, which is always really stimulating. You come away with lots of new ideas. Today, I'm going to present some results on the physical chemistry of this interface between nitride electrode and hafnium zirconate. The previous two speakers, Pavan and Schroeder, have explained the interests of the system. And we wanted to look at this interface basically to see how the physical chemistry of the interface was going to affect or could potentially affect the performance of Hf0-based devices, and therefore also maybe trace out a path for the materials optimization so that we can put this wonder material really into production. People who did the work, well, there's mainly Wassim Hamouda, who's doing his PhD thesis with us in CEA in Saclay. The samples, of course, were done by NAMLab, so Claudia Richter and Uwe Schroeder, and we thank the funding agencies. Here's the summary to begin with. Well, that'll go quite quickly. I know you're very hungry. And as I said, the motivations have been already well explained. Some electrical characterization, and then the physical chemistry of the interface. And that will be done using mainly photoelectron spectroscopy as a sort of in situ and non-destructive technique. So we know that we're not really perturbing the interface by our analysis. By the motivation, when you dope hafnia with zirconium, then at some point around a 50-50 composition, you have a very strong ferroelectric response. It's comparable to the perovskites. It's robust. You have a memory window. You also have an effect of wake-up, and I think this is actually pertinent to something which was presented earlier on the AC polling. But you have this sort of wake-up effect where you have to cycle the material for about 1,000 times before it attains its sort of operational plateau. And as has been said, one of the interests of using a hafnia-based, ferroelectric hafnia-based materials is that the optimum response, ferroelectric response, is around 10 nanometers. It's between about 8 and 15 nanometers. So it's CMOS compatible. You can put it into the production line today. And furthermore, it's 3D integratable. In other words, we don't have this problem of depolarizing field. So this is why people are, and particular industries, is very interested in it. But then, having this wonderful material, there comes a problem. And the corollary is what? That with such a thin layer, then the role of the interface potentially becomes absolutely determinant in defining the electrical properties. So you've got to be extremely careful about what's happening on the level of the interfaces, and that was the reason for this. Work. So sample preparation, it's done by ALD using usual precursors with a very short, sharp crystallization anneal following the deposition of the top electrode. Now look at the top electrode. This made life a bit complicated for us. It's very thin, and that's because this analysis was used using laboratory X-rays, and you need a very, very thin electrode to see underneath it. So we need to be careful about the continuity. Here you have the electrical characterizations. The pristine sample, sort of as deposited, is in red. You can see the slight pinching. You can see the double current peak. And then when you cycle, you get a much more classical ferroelectric response. The results here are only on the pristine sample, but they will nevertheless demonstrate the idea of looking at the interface chemistry. Photoelectron spectroscopy, photon in and electrons out, and we can look at different parts of the spectrum, in particular the core level, which carry the signature of the local chemical environment. And we're looking at a buried interface, so underneath are 2 nanometers of electrode. And what we'd like to do is distinguish the physical chemistry here at the interface from the chemistry of the bulk film, insofar as you can talk about a bulk film which is only 10 nanometers thick. And to do this, there are 3 ways of doing it. You can look at the emission as a function of angle. Quite clearly, here at normal emission, we are sensitive to deeper into the film, whereas at more grazing emission, we can look at the chemical states at the interface. You can also thin this down, this electrode down using some argon sputtering, and you can also remove it using chemical etching. And we used all three of these techniques. We also use photoemission electron microscopy, and there, instead of just recording intensity as a function of energy, you actually record images, you have electron optics, and you get an image of the photoelectric current from an area of the sample, several tens of microns. And this allows you to do mapping. And in particular, if you look at the threshold of the photoemission, this allows you to map out the work function of the sample surface. And this allows you to determine whether your electrode, remember very thin, was uniform, or whether there were oxide patches or pinholes, anything which could complicate the interpretation. So the results, some CAFM results, well, topography is quite well behaved, it's quite flat. This is actually fairly uniform as a current map, even though there are some red patches. The photoelectron emission microscopy, as received sample, we got a fairly uniform work function. This is the histogram of all the work function values in this area. But it was very low, much lower than what you'd expect for tinitride. We then sputtered away the first fraction of a nanometer from that electrode, and the work function shot up to between 4.8 and 4.9 eV, which is what you'd expect for metallic tinitride. So this is also the first indication that the top of the electrode is oxidized. Looking further into the top electrode chemistry, here we have the core level of the titanium 2P and the core level of the nitrogen 1S. In this case, we have sputtered away gradually the top electrode, and the main change here is that the peak which is associated with titanium oxide is so gradually attenuated. However, it does not go to zero. So what this tells us is that effectively there is titanium oxide on the top of the electrode. Now if you look at the nitrogen, the main change as we change here the emission angle, looking deeper and deeper down through the electrode, the main change is that the peak associated with oxynitride is getting stronger and stronger. And this means that at the bottom face of the top electrode, you have not titanium oxide, but an oxynitride. Now, looking quantitatively at these intensities, you can then calculate what is the thickness of this interface layer in the top electrode, and it turns out to be about 0.8 nanometers. Turning to the film itself, we used the hafnium-4F core level, and again here we are changing the emission angle, so getting more and more sensitive to the hafnium zirconate chemistry at the interface. And what we see is that little by little there is a second signal from the hafnium core level, which is associated with hafnium 3+, so reduced hafnium, and it's getting stronger nearer the interface. There's half an oxygen molecule missing from this equation. If you create an oxygen vacancy, then what happens is that you remove the oxygen atom and the electrons lodge on the neighboring hafnium atoms, reducing them. So from the reduced hafnium intensity, you can deduce, as a function of depth, because we have the depth sensitivity, the oxygen vacancy profile from the interface going into the film. And this is what we get. We get a very high concentration, almost 1% oxygen vacancies, going down to almost zero in the film itself. A confirmation of this comes from our chemical etching experiment, where before etching, we saw, on the previous slide, a significant signal from reduced hafnium. After we'd etched completely the electrode away, this signal has disappeared, confirming again that the reduced hafnium is at the interface with the tinitride. We can even look at the bottom interface if we etch further. And when you etch further, what you see from the two core levels, which give you information on the bottom electrode, we have no longer the oxynitride signal, which was present for the top electrode, but what we do have is a continued presence of titanium oxide. And this means that although the capacitor structure is symmetric, it's tinitride, hafnium zirconate, tinitride, the interfaces are asymmetric. And this comes from the process which by ALD, first of all, the bottom electrode is going to be oxidized. This creates a passivating layer, and there can be no further exchange between the bottom electrode and the hafnium zirconate grown on top. Whereas at the top interface, the last layer is hafnium zirconate, and then the tinitride comes down, and there can be an immediate matter transfer exchange between the top electrode and the hafnium zirconate. And this is important for the characteristics of the devices. Finally, we tried annealing. These are temperatures, of course, are totally unrealistic for real devices because we want back end of the line. We want something which is, we can put down devices on top of CMOS without melting the interconnects. So you would never do these sort of temperatures. But what we wanted to see was the effect of temperature. And these temperatures shifted, gave rigid shifts in the electronic structure, which basically translate a variation in effective doping, so N-type doping. But this time, it was happening in the bulk of the film. So we can also control the doping level of these films. And we can use the photoemission results to calculate the Schottky barrier height. And this is basically what we get, which is quite a high barrier. We're still looking into this because it is very high, and it may well be that we're looking at a barrier height between the Hf0 and these very thin interface layers, and of course that is absolutely crucial for determining, for example, leakage current in a working device. And then finally, now what we're doing is we're using much harder X-rays because 2 nanometers of a top electrode is really difficult to do. When we use much harder X-rays, we can have like a 10 nanometer thick top electrode. And if we do things right, this is a photograph of the sample, we can wire the samples up, and we can look at the response as a function of polarization. And this is what we've done, some preliminary results. The work was done at the Spring 8 synchrotron in Japan. And by solving Poisson's equation in the film, we can actually map out the potential across the film, and we can see the effect of the interfaces, giving the barrier height variation, and we can see also what the potential looks like inside the film, and that comes directly from the photoemission analysis. Okay, so those are the conclusions. Top tinitride electrode scavens oxygen. It reduces over a couple of nanometers. It reduces some of the hafnium. This gives a very strong oxygen vacancy profile, which is connected to the wake-up phenomena that have been observed. And it also gives rise to an imprint in the polarization. If you anneal, you can decrease the Schottky barrier height. And now some of the future work will be on the after cycling, looking at how this physical chemistry is going to evolve as a function of cycling, realistic cycling going up to 10 to the 6, 10 to the 7, 10 to the 8 cycles. And thank you for your attention.
All right, we have time for a few questions.
So you mentioned about the differences between the top surface and the bottom surface. So do you know then what is the built-in voltage due to that difference for the film?
Yes, we have it. This, as I say, it's a preliminary result. We have to confirm it, but this gives us an idea of you can have here you have the potential difference, so you can calculate what the built-in voltage is.
Other questions? Oh, yeah.
So can you comment about how this, there is a width to the Schottky barrier also, right?
Sorry?
There's a width to the Schottky barrier, not just the height, like you showed in this schematic.
That's
so
just,
So can you show? Can you comment on how you distinguish hafnium 3+ in your XPS profiles versus the effect of just a field?
This wasn't the subject of really the presentation, but just in a couple of words, what was done here was that we carried out the analysis, the core level analysis. We could distinguish between the hafnium 3+ and the hafnium 4+. We know that this hafnium 3+ is at the interface, and so that provides us with this part of the curve. It provides the boundary conditions for solving the Poisson's equation and getting out the potential profile inside. So it's a bit iterative. First of all, we have the high resolution photoemission. That gives us the chemistry at the interface. The chemistry at the interface gives us the amount of charge, and with the amount of charge, you solve to get the potential inside the layer.
Any other questions? All right, last one.
Did you measure the time dependence or the change of the time of this structure?
No, not yet. We would need to get good statistics. I mean, the data acquisition times are minutes. Okay, so for the moment, it would be irrelevant trying to get the time dependence of the switching.
All right, let's thank Nick and all our speakers this morning.